Good afternoon, everyone. First, I would like to thank the organizer to give me the opportunity to talk about my work. So today I am going to talk about dynamic of magnetic monopoles in presence of domain walls. So the first question that arises, what are these magnetic monopoles and what are these domain walls? So these magnetic monopoles, like magnetic monopoles, have not been fundamentally observed as a fundamental particle in the universe. So let's say if you have a bar magnet which have two poles, if one divides this bar magnet into two parts, we don't get separate monopoles. Instead we get a smaller dipole. And here comes the condensed matter system, that is frustrated magnets, to our rescue, where the excitations out of the ground state behave as magnetic monopoles. And one of the famous example is a spin ice material. So what are spin ice? Spin ice are compounds basically of the formula A2B2O7, where A is the magnetic ions, and these magnetic ions reside on this pyrochlore lattice, and because of the non-magnetic ions, these black dots, the spins of these magnetic ions are constrained along this local 111 direction. And because of this constraint, in the presence of ferromagnetic interaction, the ground state of this spin ice compounds turns out to be a state where two spins are pointing in and two spins are pointing out of each tetrahedra. And excitations out of these states is just the spin flip excitations. Let's say if one flip this spin, then it forms a 3 in 1 out state. And this 3 in 1 out state, these excitations behave as magnetic monopoles, and this was first shown in this paper, Magnetic Monopoles in Spin Ice, by these authors, Claudio Mosner and Sondi. And so what happens is, these monopoles, in presence of staggered magnetic field, these monopoles crystallize and form a ordered lattice, and this ordered lattice is called this FCSL phase. Now this FCSL phase, one can see you have some kind of, it looks like ordered phase, but on the outside it is ordered, but inherently it has some fluctuating part also, and that can be understood via fragmentation. So via fragmentation one can note that this FCSL phase breaks into two parts, where one part is a divergence full part while the other part is divergence free, like the flux coming in is equal to the flux going out. So the divergence full part correspond to this magnetic order, while the divergence free part correspond to this fluctuating Coulomb liquid part. And now the excitations out of this FCSL phase, this becomes spin flip excitations again, and it becomes this 4 in charges. So I am going to study the dynamics of this excitations, these monopoles, in the presence of now the domain wall. So now since we have this magnetic order present, because now I have an order, so we can have two different kind of order, and the region separating between them will be the domain wall. So what are these domain wall now? So I have this FCSL phase where this red tetrahedras are this negative charges and blue are the positive charges. Now if I pass a plane that cuts this whole system into two half and flip all the spins that are above this plane, now what will happen? This blue, which was previously 3 in 1 out, it will flip to 3 out 1 in. So this blue one will become now a red one. So now I have two different domains, where in the lower domain the down tetrahedra is in blue state, while in the upper domain the down tetrahedra is in red state, and we have this interface that separates between them, which act as a domain wall, and this domain wall have this mixture of this both kind of tetrahedra. And the effective diagram looks something like this, where I have region D and region D bar, and if I do the spin flip excitations, I am going to study the dynamics of this. So what we found that, so this plots that I am going to show, it's for system size 72, and this domain wall is in the center at 36. So what we found, like for one kind of charge, the probability of finding those charges at some distance g, perpendicular distance from the domain wall, like before just the z equal to 36, it has some probability, but just after crossing z equal to 36, the probability goes to 0. So, this correspond to 4 out charge moving, and it encounters reflection from the domain wall. While for the other kind of charge, that is a 4 in charge that is moving, the probability of, there is a probability of it crossing the domain wall and going to the other region D, and it gets confined in that region. So, what we observed, like when the domain boundary is made up of 3 in 1 out tetrahedras, then the 4 out moving defects encounters reflection from the domain wall, while when the domain boundary is 3 in 1 out and the moving charge is 4 in, it suffers transmission behavior. So, this is very analogous to a diode effect, but diode effect for the magnetic charges. Now, since we have seen the diode effect in this case, so can we have some magneticity based device also? So, one of the like proof of concept that we have shown is for the magnetic capacitor device. Like let us say now we have multiple domain wall into the system and we create multiple charges into the center of the system, and then we looked at the evolution of these charges. So, what we expect now from the diode behavior, like one kind of charges will go to the up direction while the other kind will go in the downward direction, and it will get accumulated at the edges, and that is what we found in our simulation. So, in this simulation the color shows the density of those charges, and as one can notice at the start of the simulation, the charges, they are like all the charges are in the center and then it starts to drift away. So, one kind move to the upper edge while the other kind move to the downward edge, lower edge, and then it gets confined on that edges. So, this shows one proof of concept for a magnetic charge storage. So, to summarize our work, so the main key finding is that domain wall act as a magnetic diode in the FCSL phase of spin ice, and using multiple domain walls it is possible to store magnetic charges at the edge of these materials. So, and it is not just theorist's dream. So, there are possible candidate materials where it is possible to show this behavior. However, the main challenge is to pin those domain walls, like does not allow it to fluctuate. And I would like to thank my collaborators, Professor Sumiran Pujari and Ludovic Jobert, and thank you.
Thank you. Thanks a lot. Yeah. So, any questions? You have still 1-2 minutes. Questions? No.
So, okay, I can ask.
Yeah.
Okay. So, like, how you could say it's a nano pole, like?
It's monopole.
Yeah, nano monopole, right?
It's magnetic monopoles.
Monopole.
Yeah.
So, like, so you have a large magnet north and south, right? Then
Yeah.
like the size is small. And how is it formed? Like, can you explain?
No. It forms in this spin ice compounds, like yeah. In this spin ice compound, where now I have magnetic ions that resides on the corner of this tetrahedras, and you have this spins. Okay. So, the ground state of this spin ice compounds is 2 in 2 out, where for all tetrahedras you have 2 spins pointing in and 2 spins pointing out. This is the ground state. Now, if I flip one of these spins, so it creates this excitations, this 3 in 1 out and 3 in 1 out, and on the neighboring tetrahedras 3 out 1 in. So, these like quasi particle excitations, their effective description is given in terms of these magnetic charges, magnetic monopoles. Like you can write this Q1 Q2 by R, they show this Coulomb interaction. Yeah, so it's emergent monopoles, not the fundamental monopoles.
Okay, thank you.
Yeah.
Thanks a lot.
Yeah.
So, let's move to the next.
Yeah.
To the final talk, some of the final talks of this QMAT 26, and I am Subroto from IIT Kanpur. So I will be talking about topological random alloy. Okay. So as a condensed matter physicist, we often deal with many degrees of freedom comes together and behave collectively and give rise to a lot of emergent phases, novel phases of matter. And in this QMAT, it has been a wonderful 4 days discussing lot of novel phases of matter in this beautiful campus. So one of the interesting phases of matter is a special kind of insulator which in a periodic boundary condition doesn't have any state at zero energy, but if you have a boundary, you have a states near Fermi energy. For example, if you consider this insulator where bulk has gap, but the boundary has chiral edge state that give rise to a quantum Hall effect, without any magnetic field, and these are known as Chern insulator or quantum anomalous Hall insulator. And the special thing about this is that they are stable as long as your bulk gap is still remain open and you don't break any intrinsic symmetries of your system. That's why these are known as topological phases of matter. But in search for those materials that actually exhibit these kind of features, people generally studied topological band theory, where all these studies have been made in crystalline order in stoichiometric system. But what if you are away from perfect stoichiometry? For example, let's take a lattice and randomly dope with a different orbital. Like you have this lattice of blue orbital and you start doping with a red orbital here, and this kind of system, like if you have just a free fermion without any topological phases, you expect it to localize immediately because of the prediction from the scaling theory of localization. But is there anything special if you have topological properties in the fermion? Okay, and that's not really a theory questions only. Even in photonic lattice, this Chinese group has shown you can actually create a substitutional binary alloy using two kinds of orbital in photonic lattices, right? So with the teasers, this is the outline of my talk. I will define what topological doping means and what are the exotic features in such topological alloy system before concluding my talk. Okay, and this is based on this preprint where I wrote with Aziz from IISER Kolkata and Adib from IIT Kanpur, and any feedback and comments are welcome because this is just a preprint. Okay, so let's define the alloy landscape first. So we have this host insulator and we have doped with D dopant. So let's take this Hamiltonian. So when you have only blue, only clean insulator of this host, you have this Hamiltonian with parameter 2 minus mh on-site potential. Now when you dope, this D has 2 minus md sigma z. That said, md is the parameter of the dopant. Now what are the phases in the clean insulator when there is no dopant? This has three different phases. One is trivial insulator, and 0 to 2 you have Chern insulator with +1 chirality, and 2 to 4 you have Chern insulator with -1 chirality, and all the other regions are trivial. Now we always choose MD to be 1. Okay, so MD to be 1 means somewhere here. Now if you have substituted all the blue atoms with red atoms, you will get H0D1, and that will always lie in C equal to +1. That's why we call the doping to be a topological doping, right? So what one expect is that if you start doping, those red patches will create small domain, and at some point it will proliferate the full system and give rise to a percolation transition. That's when you expect that the system will get the property of the dopant, right? So let's see what we find. What we find is that is indeed true if you look at the transport in sigma xx, which is the longitudinal conductivity, and sigma xy, which is the transverse conductivity. And if you look at the very large value of mh, indeed the transition happens near the classical percolation threshold where doping density is 0.6. But as you go down on mh, your trivial region become topological with quantized sigma xy even below the classical percolation threshold. For example, if you consider this cut mh equal to -1, you can see the transition happens at rho equal to 0.3, right? Another interesting fact is that if you start with a topological phase with opposite chirality, at some density it will become the chirality of the dopant, but in between they goes through a metallic phase. So you can see in this region the sigma xx, the longitudinal conductivity, is increasing with system size and giving rise to a metallic phase. So why does these things happen? Let's look at a single dopant first. Okay, so if you look at a doping, the topological doping, in contrast to a doping in a semiconductor, what happens is that you get both the donor level and the acceptor level at the same time. And these level are actually a current loop instead of a one-year charge center. Okay, and why these current loops appear? Because if you have a finite domain, you will get a edge state going from c equal to 1 to c equal to 0, and as you decrease your domain size, this edge state will still remain there, and these current loops for a single dopant is actually a remnant of the chiral edge state, right? Okay, so we have edge state. What's next? So what next is that if you have a two dopant at a different position at angle theta and distance r, those two current loop can hybridize, can tunnel between each other even if they are at a large distance, and those tunneling is actually a generalized hopping of a Chern insulator. So even if they are at a large distance, even if they are at a finite distance, they can create an environment which can give rise to a Chern insulator chunks. So that we can see in the local Chern marker, which actually calculate the local magnetization, local Berry curvature in the system. So you can see even if rho is 0.28, you can see lot of these red chunks which giving rise to a topological domain in the system. Now across this line, as you go through as you increase your rho, your domain grows and they merge with each other, and they can give rise to a global edge state in the system and triggers a topological phase transition even at low density, even if your actual dopant have not proliferated in the system, but your emergent domain can percolate in the system, give rise to a topological phase transition. Okay, what about topological host? So topological host, what happens is that the domain, there are two kind of domain, one from the host, one from the dopant. Both have topological phases. So what happens at the domain boundary is that there are two co-propagating chiral edge state that give rise to a metallic phase in the system. So this metal actually arises because of the interdomain tunneling of the edge state. Okay, so what is special about this metallic phase is that it doesn't have any symmetry restriction, because Chern insulator can be stable in class A without any symmetry. So this metal can actually survive in class A, right? So not only that, this also give rise to a lot of like rich playground to play with, to actually do a interacting systems also. For example, if you consider local moment with those dopant and you have host has also a spin, what happens is that you can have magnetic ordering, or how does a Kondo physics play out on those systems? Okay, so with that, yeah, probably the last slide is not working again. Yeah, so okay, maybe, yeah, so basically I wanted to thank these four guys because they are also sharing the final talk of QMAT, so that I don't feel alone. Okay, and so thank you for all the audience and for all the volunteers. It is not a easy work for them.
Okay. Yes, super. Thank you very much. Thank you. I think any quick question? So can you give one example where this topological doping have a host and dopant?
So actually this can happen in this magnetic topological insulator. For example, chromium, vanadium doped quantum anomalous Hall insulator. You can.
In that case, actually, those are itself is a topological insulator. And
Actually, you are. But yeah, but you
But here you said you have a non-topological host.
Yeah. So basically, this alloy experiment, probably. Okay.
So you talked about your
experiment. Yeah, this is a photonic lattice experiment. They actually shows. Yeah.
Okay, I think let's thanks all the speakers in this sessions.
Thank you.
And we close the session. Thank you very much.